Okay, hello everyone. I hope you can see my slides and you can also hear me clearly. If not, let me know. Okay, so last time we were talking, we started our new chapter, our new topic about processes, and we were talking about what a process is, and when a process is, then when a program is loaded from disk into the memory, it is called a process. It occupies memory space, and that memory space can then be divided into different sections like text, data, stack, and heap, right? And then we also talked about what are the different states of a process which it can assume during its lifetime, and how different how transitions happen from one state to the other. Uh, then we also talked about what are the different queues involved in scheduling processes and how a process moves from one queue to the other queue when its state changes, let's say from ready to waiting and so on, right? Today we are going to talk about how processes are created and how processes can be terminated in operating systems. But we will basically focus on Linux operating system. Uh, so these objectives are same as the last time, and outline is again the same. So I'm not spending the time on this slide. I'm directly going to the process creation. Uh, so when in operating system, what we can do is that we can allow one process to create other processes. And the creating process is called a parent process, and the processes which are created, they are named as children process. And they are related to each other. And to represent their relationship, we use a tree data structure or a tree representation. So, for example, here in this figure, we have a process indicated by a node named as systemd, and each process here in this figure, it is assigned a process ID or PID. For example, the systemd process, which is also known as system daemon, it is assigned the process ID of 1. And then actually this is the process in Linux which is responsive, which is like first process created when you reboot the operating system, or when you boot the operating system. And then this process is responsible for starting all the services, whether they are provided through system level processes, or they are also responsible for managing or creating the user level processes. So for example, here in this figure, you can see that this parent process has two children process. What is the one is the log indi, which is given the process ID of 8415, and then the other process is sshd, which has also which is given a certain process ID. Then it has also the some processes, for example, in this case Python. And then each of these processes, children processes, they can also create new processes as their children. So what happens is that at the end we have a tree where and in this tree data structure or in this tree representation, we can see all the processes are related with each other in a relationship of like parent and children. So systemd, it is the first user process created, and it is the root parent process for all the user processes in your system in case of Linux. So actually, in Linux, you have a command ps3. If by using this command, you can get the process tree or a tree of all the processes which are currently running in this system. For example, if in my case, if I do ps3, I can see that the different processes are running, and here I can see that systemd is the root or the parent processes of all the processes running in the system. So how we actually create processes? Uh, when we create processes, we will talk about what a system calls we can use to create the processes. But at the time of the creation, processes are assigned a process ID, and this ID is used to identify the processes and also to manage the processes. Uh, when a parent process creates a children, then we have certain options available. in terms of resource sharing, one option is that parent and children they share all the resources. Second option is that our children can share subset of parents' resources. And the third approach can be that parent and child they do not share any resources. So definitely each of these approaches they have their own implications. For example, if we say that parent and children they do not share any resources, it means that an operating system assigns a new set of resources to the children processes. So which means that we are putting more pressure on the system resources. On the other hand, if we are if we say that parent and children they share all the resources, then it's mean that parent and all its children they are competing for the same set of resources, although we are not putting more pressure on the operating system to set aside the resources for newly created children processes. So this third approach is like kind of middle ground where we say that okay, children can share subset of parent resources, and then other resources which they need they can be assigned by the operating system. Similarly, in terms of like, just like we said that we can follow different strategies or different options when it comes to sharing the resources between parents and children. There are also different options which can be adopted or which can be followed when it comes to the execution of the children. So, for example, one option is that we can allow parent and children to execute concurrently. The other option is that we can require the parent process to wait until all the children processes are terminated or they have completed their execution. Again, it depends upon your requirement. For example, if there is a case where children processes are coordinating to complete a task and they need to like for example generate result for partial computation, and the parent process then takes that partial computation and finds the final result of the computation. Then in that case, yes, parent need to wait for the children to finish their execution, and then the parent can take the partial solutions or partial computation. But in the cases where there is no such requirement for coordination between parent and the children, then we can set the strategy where we can say that okay, parent is not going to wait for children to complete their execution. For example, where children need to do some computation independent of each other or independent of the parent. Similarly, when it comes to the question of sharing the address space is like uh, remember last time we said that when a process is created, it occupies memory space, and that occupied memory space is divided in different sections like text and data, heap and your stack, right? So when the question is like when a parents create a new child, so that child, is it going to use the same memory space or not? No, it is not going to use the same memory space. That is like for sure. Every process has its own memory space, irrespective of whether they are related in a parent-child relationship or not. Okay. So irrespective of that, whether the children, whether the processes are related with each other in parent-child relationship or not, all the processes have their separate memory space. However, when a child is created and it has its own memory space, what should be the content of that memory space? One option is that we exactly duplicate the memory space of the parent into the memory space of the child. And this is like we call it as like address. We are duplicating the address space of the parent. So both parent address space and the child address space, they are exact copies of each other at the time when the child is created. And after that, the child will definitely the changes with the child process will make in its own address space or in memory space. They will not affect the address space of the parent. And similarly, once the child is created, the changes made by parents in its own address space will not affect the address space of the child. But at the time of the creation, the address space of the child is exact. One option is that we can make the address space of the child exact copy of the parent address space. The other option is like at the time of the creation, after creating the child, we can load a new program in the address space of the child. So at that time point, the child address space becomes totally different from the parent address space. We will see examples of it. So then when we will have concrete examples, so it will become clear to you what we mean by copying the parent address space into the child address space, or what we mean by loading a new program in the address space of the child. So here we have uh, we let's have a look at this figure, which basically tells us basically walks us through the creation of a process. So let's say you have a parent process, and this parent process then invokes a system call, which in case of Linux is fork. So the job of the fork is to create a new process. So it will create a new process, and this new process will be a child process then. So the fork system call, when it is executed, it returns a value, or it returns a number. So since it returns a number, so uh, okay, let me first go through. Okay. So it returns a number, or it returns a value, and that value is either zero or the ID, process ID of the child process. So since uh, the value which is returned by fork, the value seen by the parent is the process ID of the child process. But again, the same code is also, because remember we said that one option is that when a child is created, the parent address space is duplicated into the child address space. Which, what does it mean? It means that at the time of the creation, child runs exactly same code as the parent process. So since they are running the same code, the child also has this system call in its body. And in its body, the fork also returns a value, right? But the difference is that if it is the address space of the child, the fork returns the value of zero. But if it is address space of the parent, fork returns the process ID of the child process. We will see examples, and then it will become clear to you. So then, since same program is running, then depending upon what value is returned, we can actually write the code in such a way that we can that the execution of the parent and the execution of the child process, they can take different path. For example, we can say that if the process ID, the value of PID is zero, it's mean that this is the address space of the child. So in the address space of the child, because value of PID is equal to zero, so we can say, okay, execute. This is again a system call. Fork is a system call. Execute is a system call. This system call is basically used to load a new program in the address space of a process. So for example, when you simply fork, this is the result of fork. Parent address space is copied into the child address space. But when you want to load a new program into the address space of a process, for example, a child process, then you need to make a call to the execute system call, this one. This is again, we have not shown here any parameters, but when we will have an example, then you will see how it works. So when you invoke the system call, a new program will be loaded and it will start executing. And then at the end, when the child process calls exit, it terminates. On the other side, uh, parent, after invoking fork, it will receive the PID, and that PID will be greater than zero. So it's mean that we can simply test the value of the PID, and based on that value of PID, we can define a different execution path for the parent. And we can require the parent that, okay, you need to wait. So wait mean it is waiting for the child process to complete the execution. So once the child process exits it, and it sends its exit status back to the parent, then after that, parent can continue its execution. So here it is basically waiting for the child process to complete its execution. We will see examples, so don't worry. Uh, so fork, this is a system call in Unix or Linux operating system, which Unix like operating, like for example Linux, which creates new processes. a new process. Execute system call, it is used after a fork to replace the process memory space with the new program. So if you don't call execute, if you don't call this one, then new program will not be loaded, and then parent and the child, they will be running exactly the same program. Parent process will wait. We call wait, which means that it will be waiting for the child to terminate, and child process or any process can use the exit to terminate its execution, its own execution. Okay. Yeah. Let's have a look at this program. So, for example, here we have defined simply a variable n of type process ID. So we'll use it to store the ID of a process. And then in this program, we are saying n is equal to fork, right? So which mean that, okay, so when this program starts running, so it's mean it is a process, right? So this is a process itself. Let's say I'm naming it as process A, right? So process A is running. You define in its address space, you have a variable n, and then you say, then you are invoking the system call fork, which means you are saying, okay, create another process. So which will be the child of the process A, right? So I'm naming it as, let's say, a new process will be created. Let's say process B. So, but this fork will return a number. So again, remember that when we invoke the fork, a new process is created which has exactly same address space as the parent, which means that process B will also have exactly same code. It will also be running exactly same code as process A, right? But where will its execution start? Its execution will start at this point. So when the process is created, its program counter is at this point. This statement is being executed. So both, it's mean that both process A, let me draw here, process A and process B. So when process A executes fork, it will create a new process, and the ID of that process will be returned in n. Let's say the ID of that process is, I'm just making a number, 100. Okay. So it will get, so this is process ID of the process B, right? So value of n for process in the address space of process A will be 100, but the value of n in the address space of process B will be 0 because it is the child process. So fork will return 0 in address space of process B. Now, based on the value of n, we can differentiate between the parent and the child. So here we are just doing first the error handling, because fork always return a non-negative number. So if n is less than 0, then we are saying that fork failed and we exit. Else if n is equal to 0. So if n is equal to 0, then it means 1. When we have n is equal to 0 in the address space of the process B. So we are saying basically that execute whatever we have in this if block only if you are a child process, right? Because only child process will get the value of n equal to 0. And here we are making the system call execute LP. Mm, yeah, so execute actually is the system call, which you can use to specify the program which you want to run in the address space of the process B. And here you are saying the program you want to run is ls program or ns utility of your operating system, whose job is only to list the files in your current directory. So here you specify the first you specify the path to the program, the path to the binary which you want to run, name of the binary itself, and any parameters. And the list of the parameter must end with null. So this is the path. This is the name of your binary, and it doesn't take any parameter, but you must have one parameter which is null. If you have any other parameter, they will be like comma separated before null. Okay. So basically what you are saying here, that if you are process B, then then load a new program. And when you do that, the address space of process B will become totally different from process A. Let me finish this and then I will take questions. Someone sent a text in the chat box. And what is this else? This will the control will come here only in the case of parent process, because here we said if n is equal to 0, but in case of parent n is equal to 100. So here we are saying wait for null. So here we are saying wait for the child process, and null basically mean when you call wait, you can specify here a buffer or an address of a location in memory where you can get the status of the exit status of the child process. We will talk more about wait later on. So for now, just keep in mind that we are using wait to indicate that the parent process will wait for the child process to complete its execution. And once it is completed, child is completed, then it will print the message child completed, and then it will terminate. Okay. Okay, what's the question? Does the fork part of the child process return 0 because the child process has the address space of parent process when it's initially created? Uh, your question is like kind of how to, okay, let me break it down. So this statement is true that the child process has the same address space. When we say the same address space, it's mean the exact duplicate of the address space of parent. What does it mean? It's mean when you say when you say same address space and when you say duplicate of the address space, these are two different things. How these are two different things? So for example, let's say this is your parent process A, uh, or it is process A, let's say, and this is the memory address space or the address space of the parent process, right? Now, it's mean that whenever process A executes, it executes the code from its text segment here, right? In the text segment. And whenever it puts data, some local variables, it puts on the stack here, right? And whenever the data is like dynamically allocated, it is allocated from heap, right? Now, when you make the statement that process B has exact same address space, it's mean what you are saying is like the code of the process B is also located in the same memory location. And whenever it wants to make any local variable, they go to the same stack. And whenever it makes any dynamic memory allocations, those memory allocations are made from the same heap, right? This is the meaning of stating that process B has same address space as process A, which is never true. True processes never have the same address space, like typically, right? By default, they don't have the same address space. What happens when you do the fork is that process address space of process A is copied or duplicated, and then it becomes the address space of the process B. So when you do the fork, what happens is that this whole address space of process A is copied into another location in memory, let's say here, another part of memory, which has exact same copy. Everything is same. Even your program counter is same, right? So like at the point where you are where you are currently executing, but then it becomes the address space of process B. Now process B executes from this text. Process B makes any local variable in this stack segment, and any dynamic allocation is made from this heap segment. Okay. So so one part of your question was like uh, child process has the same address space of parent process. It is not 100% true. You can say child process has the duplicate of the address space of the parent. One thing. Second, your second part of your question is like fork part of the child process returns 0 because the child process is the same. No, it has nothing to do with that because the parent it is a way of operating systems to differentiate between the parent and the child. So any process which is created which is created newly created, it will return 0. So For example, in this case, in this example, we have n, right? N is a local variable, right? So if this is the process address space of process, say we have n here defined in stack, right? And when we duplicate, when we say fork, so then this address space is created, this one, and it also has value of n, a variable of n. But what is the value of n in two address spaces? An address space of the process, say it is set to the ID of the process B. So for example, 100. Sorry, I cannot write it clearly here. But after creating the process, here the value of n is equal to set equal to 0 because process B is the child process. Does it make sense?
Yes, thank you.
Okay. So many annotations. Let me delete them. Okay. So here is like the animation of the same thing which I tried to draw earlier. So for example, when you are saying n is equal to 4 and you are in the, we are looking at the address space of the parent. So parent in its address space has the variable n, but what is the variable of n before fork? We don't know, right? So, and ID of this parent, ID of this process, parent process, remember at initially we have only a single process, right? And let's say the ID of this process is X, right? So now when fork is executed and our uh, execution moves to the next statement, so at this point fork is done, right? So a child process is created and it has exact same duplicate of address space as the parent. So this was it had the process ID of X and it has child has process ID of Y. But the variable n in the address space of parent is set equal to Y because it is the ID of the child process. But the variable n in the address space of the child is set equal to 0. So after fork is executed. And now when, for example, if n is, when the control comes here, so if n is equal to 0, so it's mean that this will be executed only for the child because in case of the parent, n is equal to Y, it is not 0. So then we have executed this line, execute LP, right? You can go and read what LP stands for. I think it stands L for list and P for parameters. So list of parameters. Uh, so, okay, let me select the pointer. So when you execute this system call, so what happens is that uh, after execution of LP, the address space of the child is no more the same or no more the duplicate of parent. Why? Because we have loaded a new program which we want to run in the address space of the child. So though it's, I mean, process ID remains same, but it has its own address space, which mean basically that now the content of its memory space is totally different from that of the parent. Okay. Still, it has in the memory space, it still has the same segments. Same segments mean it has text segment, data segment, heap segment, and stack segment, but content of those segments are now totally different from those of the parents, because we have loaded a new program. Okay. If you have any questions, let me know. So here we are going to have a look at an animation to understand how fork work. So let's say we have a process which we are naming as parent process, and it is currently running on CPU. So program counter is, let's say, pointing at this statement and is equal to fork. So parent process has its own different segments in there in its address space. It has stack segment, data segment, text segment, heap segment is not shown. Okay. So let's say that program counter is currently pointing at this n is equal to fork, right? So on the cut, so this is like on in the user space. In the kernel space, we are maintaining the process control block for each process, right? And let's say this is the process control block for the parent. So we are holding ID of the process, which is X for this parent process, and we are also holding the value of PC, which is pointing to the statement where we are going to execute n is equal to fork. Okay. So this PC is your program counter register, and this PC is simply the copy of that program counter register stored in the process control block. Okay. Does okay does the n value for the child get deleted after execute LP? Uh, yes, yes. If you load a new program, and then everything will be overwritten and will be gone. Okay. Because n actually, and where did n come from? It came from the address space of the parent, right? So when you load a new program by executing execute LP system call, you are loading a new program which will have its own local variable, its own code, uh, its own content of stack segment, and so on. Okay. uh, so now let's see how things progress as we execute the parent process. So let's say that when the fork is executed, so what happens that as a result of this invoking this API, the system call for the fork is executed in the kernel space, right? And when it is executed in the kernel space, we first create the process control block for the child process. We also need to set value for its PC and PID. So when a process is created, we assign it a ID. Let's say the ID of the new process being assigned is Y, but we don't have yet set the value of the PC. The value of the PC after creating the process is set exactly same as that of the parent. So both of them point at the same place, right? So if it executed n is equal to fork, so then the child will also get this value, n is a value of n. It will not execute fork again, but it will get the value of n, because it will, if it executes fork again, it's mean a new process will be created, so which will not happen. It only will get the value of n back, right? So here the in the parent address space, n is set equal to y, and in the child address space, n is set equal to 0. And then let's say we have a single processor, a single core, so we can run only one process at a time. And let's say that our parent process continues running, and child process need to wait. So if that is the case, our program counter for the parent, it will increment, right? Now remember that once after they are created, so initially they both had the same value of PC. But if the PC of the parent is incremented, it doesn't affect from that point onwards. It doesn't affect the PC value of the child process, because from this point onward, these are two independent processes. So they can go into independent processes in the sense they can follow different execution path, although they have the same code, right? So when the next statement is executed, if n is equal to 0, so this is not true. Why? Because this is the parent process. Here we see that it has n is equal to y. Else if n is equal to greater than 0, so this statement will be true. So we'll go to this else block and it will be executed, right? And then PC will get a update. PC of the parent child parent process will get updated accordingly. Now let's say that when PC was set at this point for the sorry, so what's happening? Sorry. Yeah. So let's say at this point, now the child parent process is interrupted. Let me complete this. I will take your question. Parent process is interrupted, and then child is scheduled for execution. So it gets the turn to run on the processor or on the core, right? So its PC was pointing at this point. So after that, PC is incrementing and it points to the next location, right? So here it tests the condition. If n is equal to 0, yes, that is true. So we enter into this if block. And yeah, so we enter into this if block, and this is how things happen when you when a process invokes the fork system call. Okay, now let me have a look at. So the two processes point to the same stack in the beginning, but after the child process is created, they become independent from each other. Uh, uh, no, in beginning we have only single process. But when the child process is created, after that they have their independent address space. The only the point which I'm trying to highlight is that the address space of the child is duplicate of the address space of the parent. So by pointing to the same stack, if you mean, are they pointing to the same location of execution when the child is created? Yes, both have the same value of program counter. Please unmute yourself and let me know if I understood your question correctly and if I have answered it correctly or not. Let me know.
Yeah, that makes sense.
Okay, thank you. Okay, so previously we saw that how things work at conceptual level when a process invokes a fork, but we didn't cover the part like after, let's say, forking. Let's say if child process executes and execute LP system call, which basically means it's want to load a new program into it at the address space. So let's have a look how things look differently this time. So again, we are starting from the same point. We have a single parent process. Initially, we have the process control block in the of the parent in the kernel address space. So program counter is pointing to n is equal to fork. So when fork is executed, program counter it actually moves into the address space of the kernel from where your system call is executed. And as a result of execution, the process control block for child process is also created, and its PC is also points to the same point for execution in the same point in the text segment for the execution purpose, right? And then the values of n are set. In parent, it is set equal to y, and in child, it is set equal to 0. Now, after that, let's say our parent process continues executing. So it tests if n is equal to 0, no. So it goes to the else block and enters its body. Let's say at this point it is intercepted. So which basically means that it is kicked out of the core. So then its value of PC is stored in its process control block, right? And saved in the memory. And then the process control block of the child process is loaded. And then we set the value of this PC register, same as the PC value in the process control block of the child. And then we start executing. So it tests if the value of n is equal to 0. So it turns out actually this arrow should have gone away at this point in animation. It should have disappeared. So anyway, it checks if n is equal to 0. Yes, but this time we are in the body of the if block. We are executing the execute system call, which is used to load a new program, right? So when this is executed, so we make the system call, we trap into the kernel space, which executes the body of the system call. And once it is executed, the new code is loaded. And when we say new code, we have new text, we have new text segment, we have new local variables in the stack segment, we have new initialized and uninitialized data segment, and we will also have new content for the heap. So everything at this point will look different from the parent process. Okay. Any questions? No? Okay, so actually, there is no system call with the name of execute. Execute in Unix, or for example, if you try it on Ubuntu, you will not see any system call with execute, but there are system calls. So it actually represents the family of the system calls. So there are different variants like execute CL, execute L, execute LP, and so on. I don't know what is the difference between most of them, but you can simply go and look at their documentation. So for example, in this case, execute LP, the basic difference is that how you specify the parameters. how you specify the parameters for this system call. Okay, but all of them end up calling the same kernel level equivalent of execute. The only difference is that how user passes the parameter to this execute system call. Otherwise, conceptually, under the hood, they are doing the same thing. Okay, so let's have a look at some examples about some examples of the code where we are using fork system call to create new processes and try to understand what this code is doing. Okay, so let me walk you through this one, and then for next example, I will give you some time to think about the code and try to understand on your own. So here we are initially, definitely we have only a single process. Actually, here we should have a curly bracket. So we are defining a variable n, and then we are running a loop 10 times, and then in each iteration of the loop we are saying a fork, so which basically mean that this first process creates how many children? 10, right? And then we are saying if n is equal to equal to 0 0, print hello and exit, right? And so which mean that, let's say if iteration is equal to 0, I is equal to 0, first child is created, then if n is equal to 0, it means that child will enter into this if block, it will print 0 and it will exit, right? So the child will never get the chance to go to the next iteration of for. If I had removed exit, then after printing hello, I will get that the process sorry, the child will get the chance for the next iteration, set I equal to 1 and create another child which will be basically a grandchildren, right? But here, since we are saying exit, we are terminating the child, so it doesn't get the chance to create a grandchild of the parent. And once all our children process they are created and all of them print 0 and all of them terminate, so only then our parent process continues, because here we are saying that our parent process it will wait for all of the 10 child processes to complete their execution. So how you can say that you can ask the question that how we know that this part will be executed by the parent, because for parent and this condition is false, right? And is not equal to 0, so then the execution path uh, finally reaches at this point for the parent, right? And then it enters the loop and wait for 10 processes, children processes to complete their execution. You can again ask here a question, how does a parent know that, okay, it is waiting, but how does it know that which one of those 10 children processes are completed? So for that, wait actually returns the ID of the process, child processes, which is done with its completion. By looking at that PID, the parent process can differentiate between different children processes. But here we have not saved that the return PID in any variable, but in some other example we will do that. Okay. So what is this pseudocode doing? So basically the parent process, it creates 10 children processes and then wait for them to terminate before proceeding. So let's say if 9 children processes have completed their execution, but that the one is still running, parent process cannot continue here. It will still be waiting for that 10th children to complete 10th child to complete its execution. Okay. Any questions? No? So this is actually mm, equivalent version of what is written here on this slide. I simply little bit modified it and put some printf statements to make it more understandable. So let me walk you through this code. Everything is initially same, and is equal to 0, status is equal to 0. Status is what actually when we call the wait system call here, so we can also pass it address of a variable, and in that address, the child process which terminates, it can save its exit status. So it can then tell by using that address, that memory location, it can tell the parent that, okay, I'm exiting, and while I'm exiting, I'm setting my exit status. For example, whether it is zero, or is it, for example, whether there is an error, or whether this is normal termination, or whether I'm aborted. So those kind of, that kind of information. Okay. So that's why we are defining this status. I is only for running the loop. So first the parent is printing hello from PID, and it gets its process ID. Again, I'm running this example in Ubuntu. So I don't know. It will look very different if you run it on try to run the similar example on Windows, for example, because then you need to use the system calls of the Windows operating system, right? So here I am making a call to get the process ID of the parent, and then I'm running the loop, and then in the body of 10 times, and then in body of the loop I'm invoking the fork, and then I'm saying if n is equal to 0, then in the body I'm simply putting a printf hello from process ID. So here actually I will print the ID of the child, and then I'm saying I'm exiting, and then exit 0, right? And here I'm waiting for all of them, and once the parent is waiting for all of them, and once all the children are done, then we are printing this message hello from PID. So actually we expect to see the same PID here and here, because this part is executed only by the parent, right? And here we expect that to have PID of 10 different children processes. I am proceeding. Okay. So when you run, you will have output which looks like from this hello from process PID. So this is your parent, and then these are your 10 children running, and your parent can't print anything because it cannot execute, because it is waiting for the children to complete their execution. Once all of them are done, then it's again prints hello from PID parent, and I am proceeding, right? And here, if you can see, the process IDs, they are not appearing in sequence like 70, 69, 71, 75, 72. So it is not like the process ID which has lower ID is getting that first turn to print. So which basically mean the processes are allowed, or they are allocated the output device uh, not based on their process IDs. So for example, if you run them again, the order in which they get the turn to print on the screen is will be different. For example, here 81, 80, so it's not in sequence. It's 86, 84, 85, and so on. Okay. So it is determined by operating system, because you are doing process scheduling. So which process gets the uh, chance to run on the core or to get access to the output device, it is decided by your operating system. Okay. Any questions? No. Okay. uh, uh, okay, before we continue with the next example, I have prepared a set of slides. I have uploaded a set of slides on the syllabus on our Canvas page. Let me download it and walk you through it, because it will help you to understand how fork is working in more detail, and it will make things more clear. So let me first go through it. Okay. So actually, this was a question I think in one of the exams of the previous offerings of the course. So here we need to draw the process tree that will be generated by the following code. So how we can draw the process tree? It will be, let me walk you through the process. It will not only help you to find the solution, but it will also help you to understand with more clarity how fork is working. Okay. So let me just point out some locations in this code. Uh, So we are invoking a fork here, and then we are saying, okay, if PID is equal to 0, then invoke another fork, and then it keeps iterating. If if it is a child process, it enters an infinite loop, and if it is not a child process, then we create another fork, another process, and again check if it is a process PID is equal to 0, then another fork, and infinite loops, and then another fork here within the body of the child, so it is like grandchild, and another infinite loop. So like there are like bunch of fork system calls, right? And we want to draw the process tree. So this is the solution. This is how it looks like. But how we reach this solution, let me walk you through. So initially you have only one process, right? So I am naming it as A, and this arrow actually indicates the point of execution for the process, right? So let's say initially we are at A, so we have only one single process here, which you can see here at the bottom, only one circle named A, right? So, but when you execute PID is equal to fork, after its execution, what happens? A new process is created which has exactly same address space as the process A. So we simply copy over the whole code. So process B now has the same code as the process B, and both have the same point of execution at this place, right? So, but now B is the child of B is created by A. So that's why we indicated by pointing an arrow from A to B, right? Now, what we are going to do is like both of them execute their, let's say, both of them execute their statement. So for process B, PID will be 0 because it is child. But for process A, PID will not be 0 because it is the parent, right? So its next point of execution of process A will be this statement, right? But for process B, it will enter the if block here, right? If part here. Now, what we are going to do is that we are going to freeze process A for the time being, and we are going to start executing process B, continue executing process B, right? Because otherwise, if we continue executing both of them like concurrently, it becomes difficult to follow the process of tree creation, okay? So we are, let's say we are freezing process A. Let's say you can assume there is a single core in your system and only one process can run at a time. And let's say process B gets the chance. So if when this statement is executed here, so sorry. We are freezing process B, not process. We are not process A. So we are freezing process B. Okay. So So when we freeze, so when this statement is executed here, so it's mean that A is creating another child, right? So which means that we copy the address space of A as it is, and in the address space of the process C. So and both have same point of execution A and C, right? So in the figure, we create another child, another process C, and make a pointer from arrow from A to C, right? Now, again, here we will get PID equal to 0, but here we'll get PID not equal to 0, right? So that's why A's control will reach to the while statement, while the execution of the C will enter the if block here, right? So then now it is stuck in the infinite loop, right? Now we can assume that, okay, sorry. So now we can assume that since A is stuck, now we can assume that process C gets the chance and process B is still waiting for its turn, right? So if it gets the chance, it executes this fork. So when it executes this fork, another process is created, right? Which has exactly same code as the process C. We are naming it as process D here. If you don't understand, please stop me, guys. Please. Uh, I don't want to feel like I'm talking to myself, okay? So,
So does the code on top of D like still get copied even though it's no longer being used?
please say it
The-
again.
So you see how like D is gonna start on that if PID equals 0, right?
Yeah. Yeah.
the code above it will never get executed, but that text in memory is still saved for process
Yes,
D, right?
yes, that's correct. The
All right.
code above this like D arrow will still be there in its test segment, but since our point of execution is pointing here at this location, this location, and there is no back jump in our code, so then our program will be executed in this direction. Okay. Anything else? Okay. So, uh, so another process is created which we name as D, and it has exactly the same code as its parent, which is C. So since C has created, so we put an arrow from C to D. C has created the D. So now again, what will happen? Like parent, for parent PID is not equal to 0. So parent the its point of execution moves to the end of the if block or out of the if block, which is at this point here. But for child, it enters into the if block and where it gets stuck in the infinite loop, which means that D is not going to create any more children, right? But it's we can now, let's say we continue with C. So C again says PID is equal to fork, which means it's create a new process, right? Let's say we are going to name it E, and E has exactly again same address space, so same code, and both of them have the same point of execution point, like C and E. So in the figure, we create a new node and we make an arrow from C to E, right? So again, uh, for parent, PID is not equal to 0. So we come to the end of the if block and then end of this part, and then it gets stuck. So C gets stuck here, right? And E, it also gets stuck. It enters in the body of the if block, and here again we have infinite loop, so it also gets stuck, right? So now it's mean both C and E are not going to create any more children. But we are not yet done. Why? Because our process B never got the chance to run. So let's say now process B is scheduled and it runs on the core. So its pointer was here, right? So now if this point, if yeah, it's the same thing which I have explained earlier. So while has it has moved here. So if the statement is executed and other process is created, which we are naming as F, again it has exactly the same code, and both have the same like program counters have the same values for both of them. So in the figure, we create another node, and since B has created F, so we simply put an arrow. And for the child, PID is equal to 0, so we enter the body of the if statement and F gets stuck. For the parent, PID is not equal to 0, so we reach the end of this if block, and then definitely control will reach to the next part. So where we are saying again PID is equal to fork, so another process will be created, which in this name we can case we can name as EFG, G, right? So, and again, their program counter values are same once the G is created. So, which means that they continue their execution from the same point. So, for child, PID is equal to 0. So, it will enter this block. For parent, PID is not equal to 0. So, its control will reach while 1, right? So, which means now B is stuck, but let's say now G gets the turn to run on the core. So it creates another process. So for example, which is let's say H in this case, and both have same pointers again. And for child, PID is equal to 0, so it gets stuck. But for parent, PID is not equal to 0, so it comes to the end of it don't enters the if block and reaches to the next statement, which is fork. So it creates another process. So G creates I, and then after that both point to the same location in code. So for child, PID is equal to 0, so it gets stuck in while 1, and for parent it is not equal to 0, so it comes at the end of the if and then next end of the next block and then reaches while 1. So both get stuck, right? So at the end you have this figure, this process tree of the for the example. Okay, any questions?
It's a bit to keep track of, but it makes sense.
Yeah. Yeah, but I mean, this is very helpful just to understand what the fork is doing, right? Because it is executing the same code as the parent. Every time you fork a new process, it has exactly same address space as its parent, unless you make a system call execute to launch a new program. Could you give a bit of idea about the exam, the question pattern, and the format? Uh, Okay, I can release the midterm exam of previous offering. Uh, but if you look at the schedule, we have a day where we'll go through the practice questions. Actually, I will solve that midterm exam. I can release earlier before the that day in our syllabus or in our schedule. So if you want, you can practice on your own, but you will get an idea if you go through it, how the questions will look like. Okay. But we have one day dedicated to do some practice questions or to solve one previous midterm exam. Okay, so how much time we have? We still have some 13 minutes. So let's go back to our original set of slides. Okay, so here we have a second example, and I want you to think about the code and try to understand what this pseudocode is doing. So again, there we have a mistake again. We don't have here curly bracket, but anyway, it's fine. So here we have a loop, and okay, can think about it, and you have 1 minute. Look at the code, think about it, and tell me what it is doing in terms of creating children. Like for example, how many children processes will be created. You are welcome to share your thoughts about the code. Like, what do you think? How many children processes will be created? You can unmute yourself, or you can simply text me through the chat box. Okay. Someone said two children processes. What about grandchildren? Or there will be no grandchildren?
So if I'm understanding this correctly, right, after the first iteration of the parent process, right? Will the next argument go like the child process will then start and print hello? Is that
Yes.
right?
The child
And
process will get the value of n, but it will not execute fork. So it will simply get the value of n, which is equal to 0, and then it will execute print hello.
and then it goes back to the for loop because it has that same
Yes.
code as well.
Yes.
Okay.
Yes. Yes. In previous example, we didn't have any Like that animation, we didn't have any uh, loop back.
So to make sure I'm understanding this, so we start with the one, we then fork it, which gives us two, at which point I is equal to one, and then does that mean we run it one more time and it forks into
No,
having four grandchildren?
we start with I equal to 0.
Yeah.
So the parent, the main process, which let's say I'm naming it process A, it will execute this for loop 2 times, right?
Right.
So it will create 2 children. For the first child, which is created at the time when it is created, the value of I is equal to 0, right?
Right.
And when
Oh,
that
and then it
child goes
increments.
back, yeah, when that child goes back, the first child goes back, it increments I to 1. So it also creates another child, which is like in its iteration, right?
Oh, it doesn't create two. That's right. It would only create the one grandchild, yeah.
Yeah. So
Okay. I see
let-
where I went wrong.
yeah. So let me like first go through this slide, and then if you want, I can draw the things. Okay. So uh, here the one thing is that parent is not waiting for the children. This is different from our previous example where parent was waiting for the children to terminate, and then every child creates 2 minus I plus 1 number of its children. Okay. And then it also print hello for parent and children, right? So let me go to the OneNote and clarify what I mean. Okay, someone sent a text message. 2 children with one grandchild each. Okay, someone, yeah, Jose said 2 children with one grandchild. Okay, let's have a look how things will work. Okay. We have some time, so I think we can complete this example at least. So, mm, so you have this, let's say a process A. I'm just naming it as the main process, right? And when you reach the fork, so s- and let's say I'm also creating its address space, and in address space, I am recording its value of I. So value of I is equal to 0. So when I value of I is equal to 0, it says n is equal to fork. So it creates a child which I'm naming as B. Uh, so let me put it here, B, right? So this is address space of A, and this is address space of B, right? So when address space of B, the I, it also gets exactly same value. Everything is same. So it also gets I is equal to 0, right? So let's continue with our let's freeze B and continue with A. So then when B will continue, so here after n is equal to fork, it will print hello, and then it will go back to the loop. It will increment I, so I will become 1 for A, and then it will check I is less than 2. Yes, so it will say print I again. I'm not printing those messages, so it will say n is equal to fork, so it will create another child. Let's say it creates the child C, and this is address space of C, and it gets the same value of I as parent, which is 1, right? So again, I'm freezing C, I'm allowing A to continue. So then it says print hello. then it goes to and increments I, so I becomes 2. Now 2 is not less than 2, so condition becomes false. So then this process is terminated. Now let's continue with B. So where was the point of execution of program counter? At n. So n is equal to 0, then it says print hello, and then it goes back to the loop, increments I, and I becomes 1, right? So then it says, okay, it enter I is less than 2, yes. So it says print I, and then it says fork. So it creates another process. Let's say I'm naming it as D. So I'm putting an arrow here. And this is the, sorry, this is the address space of D. And it has I, value of I, which is exactly same as its parent, 1, right? So then it says print hello, and then it's increment I again. So I becomes 2. Now 2 is not less than 2, so its iteration is terminated. Now let's say continue with C. So it gets n is equal to 0 and prints hello, and then it increments I. So I was 1, so I becomes 2 here now. So 2 is not less than 2. So C never gets the chance to iterate again, right? And now let's say we also have the D gets the chance. So for D, again, we have the point of execution here, n is equal to 4, n gets the value, print, we do print hello, and then we go back to the loop, increment I, and when you increment I, it becomes 2. Now you check the condition, 2 is not less than 2, so the loop is, you exit the loop, and your program is, your process is completed, right? So you have this process tree. You have one parent with 2 children and then 1 grandchild. Any questions? So again, I did the same thing which I did for the last example to write the actual C code instead of the pseudocode, and just put a bunch of printf statements. So you have n is equal to 0, I is your control variable for the loop. You are printing a message from the parent, like process A in our figure, and it is hello from process ID. My parent ID is, it will have its own parent IDs because who has created this one, right? And then we are running the loop for I is equal to 0, I less than 2. So here again, we are printing just control variable, process ID, and child ID. If because now we are here, we are calling the fork. When we call the fork, you will get the child, right? So then here we are saying hello from process ID, and we print the process which is executing this code, and the ID of the ID of its parent. And when we exit out of the loop, here we print hello from process ID, blah, blah, blah. So actually, I don't want you to walk through, I cannot walk you through this output. But if you keep in mind the figure which I just draw on OneNote, and then you like trace this execution, you will find, you can verify for yourself that this output is correct. Okay. And I will encourage you to do that so that you at least understand how things are going here. Okay. Any questions? What happened? Okay. Okay. Someone is like using the pointer. Anyway, any questions? No? Okay. If no questions, then that's it for today. Have a nice day for rest of your day, and see you in next lecture.
You too. Thank you.
Thank
You're
you.
welcome.